In this slide, I would like to share with you one interesting fact which called the Pascal Paradox. So the Pascal Paradox can be explained as, for incompressible fluid in a container, the pressure of a liquid at the same level remain the same. So it means that if we have a special container like this, so you could see that we have a small cylinder here, a big cylinder here, so a special cup here, so and then the non-symmetry shape here, and so on and so forth. So okay, the shape or the volume of the liquid is actually not influence the pressure. Please remember that the equation is P equal to rho G and H. So means that the three parameters that could influence the pressure is the density of the liquid, is the gravity acceleration, and the vertical height of that liquid. So means that the volume, so you could see here that the volume of water here is different according to the container, but the height is still the same. So means that if we have this situation, so all of these is same liquid. So if we have a level here, so if we have a line here, so we could say that the pressure at this level is same to the pressure at this level, and it is same to the pressure at this level, and it is same to the pressure at this level. So means that the volume of water above the point is actually not influence the pressure. The pressure of a liquid is influenced by the vertical height only. So this is the Pascal paradox. So and then, as I said, atmospheric pressure is gas. So and then the atmospheric pressure actually has its own pressure. So according to this table, so I hope you could remember the value of atmospheric pressure. So the atmospheric pressure is equal to 101.33 kilopascal ABS. So what is the meaning of ABS here? So it is an absolute pressure. So we will learn about absolute pressure later on. So means that, so in absolute pressure, so mean pressure that measure from real vacuum condition in real zero, in absolute zero, is equal to 101.33 kilopascal ABS. But we have another type of pressure which called the gauge pressure. If you are measuring the gauge pressure, we assume that atmospheric pressure is equal to 0. So please remember the previous slide when we evaluate about this one. We assume that this is the surface, the free surface where atmospheric pressure contact with the liquid. So at this surface, the pressure is P atm, which means the atmospheric pressure, but we assume it is equal to 0. Why we assume it is equal to 0? Because this is a gauge pressure. So and then it is advantage for you to remember the density of air, which is 1.225 kilogram per meter cube, and also the viscosity of the air as 1.789 times 10 to the power of 5 Newton second per meter square. Measurement of pressure. The pressure at a point within a fluid mass will be designated as either an absolute pressure or a gauge pressure. Absolute pressure is measured relative to a perfect vacuum, or the absolute pressure, the absolute zero pressure, whereas gauge pressure is measured relative to the local atmospheric pressure. So according to this statement, we found that we have two types of pressure. One is absolute pressure and another one is gauge pressure. So the difference of these two pressure is absolute pressure is measured from an absolute zero pressure, means from the vacuum condition in the space, because we believe that in our world, on Earth, we have an atmospheric pressure, but outside the atmospheric layer of the Earth, there is totally vacuum condition. So we assume that totally vacuum condition is our starting point. So means that the pressure for atmospheric has certain value. Okay, so and then the value of the atmospheric pressure is from the previous table, it is equal to 101.3 kilopascal. So and then, because in some application we are doing on the Earth, and then means that even in our body, the pressure inside our body is actually equal to the atmospheric pressure. So that's why sometimes we feel that it is not necessary to measure the atmospheric pressure, because the pressure that we have and the pressure on that certain application is same, which mean the atmospheric pressure. On that time, we could assume that the atmospheric pressure is equal to zero. So if you measure something, if you measure pressure that relative or from the atmospheric pressure value, so we call that type of pressure is a gauge pressure. So let's say if this is the atmospheric pressure, so if you assume that this point is equal to zero, your origin, your starting point, so this value is actually the gauge pressure. And then the difference between absolute pressure and gauge pressure is, in absolute pressure there are no negative value. Okay, please bear in mind that in absolute pressure there are no negative value, but in gauge pressure you will have a positive value and you will have the negative value like this. So if you have a negative value for gauge pressure, so it means that your pressure is less than the atmospheric pressure. So as stated here, if the gauge pressure is negative, so you have slightly a vacuum condition or a suction condition. So in this slide, I would like to share with you the idea of how to measure the atmospheric pressure. So in the previous table, we know that we need to remember the atmospheric pressure is equal to 101 kilopascal or 101.33 kilopascal. So the question is how to measure the atmospheric pressure. So we could measure the atmospheric pressure by using one simple device called a barometer. So a barometer is a simple device, consists of a test tube like this. If you have a cylinder like this one, and then normally previously Pascal, a scientist, used mercury to prove the amount of atmospheric pressure. So the idea is simple. First we fill all the test tube here with mercury, and then we put it into this condition, and then we release a stopper here, and then we let the mercury flow out like this. And then according to Pascal, according to this barometer experiment, we found that the mercury did not flow totally like this. At certain height, the mercury will stop flowing. So why it stopped flowing? Because there are something that push the mercury at this surface to prevent the mercury to flow out from the test tube. So this force is actually the atmospheric pressure. So and then according to this diagram, we could say that in equilibrium, so we found that the force here is actually same amount with the weight of this mercury. So and then how to calculate the how to calculate the pressure of atmospheric pressure, we start from the idea of Pascal paradox. So from Pascal paradox, so it says that for same liquid, so all of this is mercury, so and then on a same level, so we take this level, so the pressure on this level is actually remain the same for all points. So means we take 2 points here, one is point here and another one is point at here. So let's say we have a point here, so one is point at here and one is point at B. So let's say we have, this is point number 1, let's say. So according to the Pascal paradox, so because it lays on the same level, so P1 is equal to PB. So and then according to this condition, so mean this is the borderline, the free surface where the atmospheric pressure acts on this surface. So means we could say that PB is actually equal to PATM. So and then we could calculate the pressure for P1. So P1 here is the pressure because of the existence of this mercury. So we have the rho for mercury, gravity and the height. So and then because in this empty space, okay, in this empty space we have actually the vaporized mercury. So we add the pressure for P1 with the pressure of vapor, mean the pressure of vaporized mercury. Okay, from this idea we could get the atmospheric pressure is equal to rho GH of this mercury time plus pressure at this empty space, the vaporized pressure for mercury. Okay, to simplify this calculation, we assume that pressure for vaporized mercury is almost equal to 0, so it is very small pressure actually, so we could neglect the existence of P vapor. So and then we could calculate the atmospheric pressure by only calculating the rho GH, and according to the Pascal, the height here is equal to 760 millimeter. So if you calculate the atmospheric pressure with a rho G and H, so rho here is 13,600 and G here is 9.81 and H here is 0.76. We need to convert this unit into meter, so we could get it is almost 101,320 Pascal. So mean it is true that PATM is equal to 101.3 kilopascal. So this is the evidence, or the way we prove that our atmospheric pressure is equal to 101.3 kilopascal. From this experimental work, we found that if we use mercury, the mercury height is 760 millimeters. So that's why another method to show the pressure is by showing the height of this barometer. Means that if you have 760 millimeter mercury, something like this, so this actually describe the pressure. However, you cannot just use these numbers because this value is actually showing how high the mercury raised in the test tube. So what you need to do is you need to recalculate your pressure using this equation. So means that you substitute the value of mercury, which is 13,600 kilogram per meter cube, you times with the gravity 9.81 and times with the height, which is 770 millimeter mercury or 0.76. So then you could get the value of the pressure. So means that if you get, for example, 20 millimeter mercury, so you need to calculate by using this idea to get the value of then if you have for example 700 millimeter of water, so what is the pressure of this one? So the idea is same with the previous one. You just use the equation of P equal rho GH, but what you need to do is you substitute the rho of water, because we are using water here, so it is 1000 kilogram per meter cube. So the gravity 9.81 and the height is 0.7. Then if you calculate these terms, you will get one answer in Pascal. So this is the pressure of 700 millimeter water.